Alright, in this video here we're going to look at an example of an exponential growth problem. Now I did another video where I explained the formula for exponential growth and what all the variables in that formula mean. So if you haven't seen that video yet, you might want to check that one out. It's pretty short, it's only like 3 minutes long, where I just show you what the formula is and explain what all the different things that you're plugging into the formula represent. And we're going to use that formula to solve this problem. Now this one, there are 4 parts to this problem, so I have here just the first part. We're actually going to write the equation, and then we'll use that equation to answer some questions as we go along. All right, so here's my problem. The initial bacterium count in a culture is 500. A biologist finds that the relative growth rate is 40% per hour. And we want to find the function that models the number of bacteria after T hours. Sorry, I'm just looking at my notes over there, or looking at the book. Just a minute, I thought I copied something wrong, but it's not. It's correct. Okay, so the initial count is 500. The relative growth rate is 40% per hour. And we want to find the function that models the number of bacteria after T hours. All right, so if you watch that other video that I did on just the formula for exponential growth, this is what the formula looks like. N of T, the number present at time T, is equal to N sub 0, the initial amount, the amount that are present at time T equals 0, times E to the RT power, where R is the relative growth rate and T is time, right? And the time can be measured using any units of measure. In this case, since we're talking about 40% per hour and after T hours, in this problem, T is going to represent hours because that's what we're given in the problem, right? Okay, so in order to write this function, I need to find a number to plug in for the, let me use a different color here, for the N sub 0, right? So I need to know what number to put there, and I need to plug in a number for R. If I have those numbers, then I can write my function and use that then to answer questions about this particular bacteria culture. Right? So what's my N sub 0? What's my amount at T equals 0? Well, they tell us in the very beginning the initial bacterium count is 500. Right? There's my N sub 0. Right? So when I'm running this function, it's going to be N of T equals 500. All right? That's my N sub 0. That's my initial amount. All right, and then it's going to be E to the power of R times T. Well, R is my relative growth rate, which they tell us the relative growth rate is 40% per hour. Now, when we put that 40% as our relative growth rate into the equation, I don't put 40. I have to change that percentage into decimal form. Right? So if you remember, 40%, the decimal place is right here. To change a percent to a decimal, you divide it by 100, which is the same as moving the decimal point 2 places over to the left. So that's going to be 0.4 or 0.40, but I can leave off that 0 at the end. So it's going to be 0.4 times T. Right? And there is my function, which will model this bacteria culture. Right? So when you're asked to find a function that models whatever the population is that you're talking about and how it grows over time, your formula, your equation is going to look like this: N of T equals N sub 0, E to the RT. Plug in the initial amount for N sub 0, plug in the relative growth rate, the percentage, just change that percentage to a decimal, and plug that number in for R, and we've got our model here. All right, and just a quick note, why the initial amount goes here. Well, if you think about it, if you plug in T equals 0, right, so if I go to my model here and I plug in T equals 0, I would have E raised to the 0 power. What's anything raised to the 0 power? It equals 1. So I have 500 times 1, so my amount at time 0, when I plug in 0, I get 500. That's why our initial amount always goes in front of the E, because every time I plug in T equals 0, I'm going to get E to the 0 power, which is always going to equal 1. So it's this number times 1. That gives me my initial amount. All right. So there's our model that we're going to use. Now, I'm going to pause the recording here and erase this and keep the model because we're going to need that to answer the other parts of this problem. And then I'll put up the next couple parts of the problem and we'll work through it and do the rest of this problem. All right, so I put our equation that we found in part A up at the top here. N of T equals 500 times E to the 0.4T. Also on the side, just what the variables represent, right? N of T represents the number of bacteria. T is the number of hours since we started counting this population of this bacteria culture. All right, so remember, when you're writing a model that represents a real life situation, it's important to have the equation there, of course. Like, you need to have the equation, but it's just as important to have a note of what the variables represent. Otherwise, a person comes along and says, "Oh, N of T equals 500 E to the 0.4T," but what does that mean? What is that telling me about real life? Well, N of T is the number of bacteria, T is the number of hours. it's important to know those things in order to be able to use this model effectively to actually answer questions or solve problems or whatever. Right? So now that we have that, we're going to answer some questions or solve some problems or whatever. Right? So B, what is the estimated count after 10 hours? All right, so I have my equation. They give me a number here, 10 hours. So the only question is, well, where do I put that 10? Is that my n of t, or is that my t that I put up here? Right? Well, if you know what the variables represent, it's not that hard to figure out. Right? 10 hours is a number of hours. That's my t value. So I'm going to put that 10 hours in for t, and then just basically do the calculation to see what the population is after 10 hours. Right? Again, when you're dealing with word problems, real-life situations, it's important to know what the variables represent so that when you get to a problem like this, you don't put that number in the wrong spot. All right, so 10 hours, right? Hours is not a number of bacteria, so I'm not going to put it over here. I'm going to put it in for 10. All right, so I want to find n of 10, right? I'm plugging in 10 hours for t. All right, so n of 10, little poem I just wrote for you all. Hope you appreciate that. All right, so n of 10 equals 500 times e to the 0.4 times 10 power. All right, so I'm finding n of 10, which means I plug in 10 for t. And now, there's not really any solving to do here. I just need to do this calculation to figure it out, which for all of these problems that we do with exponential growth and some other ones that we'll be talking about in some other videos that I do of like radioactive decay and like Newton's law of cooling and stuff like that, they all involve an e being raised to a power, which means when it comes time to evaluate what it's equal to, you need to use a calculator. It's really not the kind of thing you can calculate by hand, unless you have a book of like a tables of exponential values of exponential functions that you can look up, which if you do, you can go ahead and use that, but it's way easier to use a calculator. All right, so 500 times e to the power 0.4 times 10. Right, notice one little thing about putting this in the calculator. Notice when I do e to the power 0.4 by 10 times 10, I put 0.4 times 10 in one single parentheses. Right? If you do it differently, your calculator may not give you the correct answer. And I get 27,299.07. Since I'm dealing with bacteria, and I can't have a fraction of a bacteria, or a bacterium, I guess would be the singular of bacteria. I round to the nearest whole number, 27,299. All right, so after 10 hours, I'm going to have 27,299 bacteria in my bacteria culture. Right now, here's the way that sometimes people type this in. I'm going to show you what happens because it's not right. I just want to make sure you're aware of it so you don't make this mistake. Right, if you type it in like this, 500 times e to the power, and then 0.4 in parentheses, and then 10 in another parentheses. Right, when I hit enter, I get a completely different answer, right, and totally wrong answer, like not even close to the right answer. Right, remember what your calculator does, it follows the order of operations. So what it's doing in that second one that I typed, it's doing the exponent first, but the only thing in the exponent is the 0.4. So it's doing e to the power 0.4, getting that result, and then doing 500 times that, and then that result times 10. Whereas what we wanted to do is multiply the 0.4 times 10 first before it does the exponent. So that's why in the first one, I have to put the 0.4 times 10 in one single parentheses. The calculator does what's inside the parentheses first, then it'll do the e to that power and do it correctly. All right, so just those little things you have to be careful of when you're typing this kind of stuff in the calculator. Mistakes I see people make sometimes, so watch out for that. Right, but if you can type it in the calculator correctly, it's not hard to do at all. Right, we have the equation here. I identify that the 10 hours is my t value. I plug 10 in for t. I type it in the calculator. I get my answer. All right, once again, I'm going to pause the recording and erase this part, and then put up part C, where we'll solve another problem involving this bacteria culture. All right, so I put the answers for parts A and B up here. After 10 hours, we had 27,299 bacteria. And now part C. Right? After how many hours will we have 80,000 bacteria? All right, so seems similar to part B, right? We have our equation already. They give us a number. Let's just plug that number in for t like we did in part B and get our answer. All right? Don't be stupid though. All right, read the problem carefully and think about what the number is that they're giving you. Sorry, I didn't mean to call you stupid. All right, so after how many hours will we have 80,000 bacteria? 80,000 bacteria. That's not a number of hours, right? I'm not going to plug that in for t, which is a number of hours. That wouldn't make any sense at all, right? N of t is the number of bacteria. So the 80,000 bacteria, I have to put over here for the n of t and then solve for t, right? I want to find after how many hours, which means I'm looking for t, Right? So once again, knowing what those variables represent, very important when you're doing a word problem, and then also reading the problem carefully so that you know the number they give you, which one of the variables is that? It's the number of bacteria, that's the n of t, so put that 80,000 over on the left side of the equation for n of t. Right? So 80,000 equals 500 e to the 0.4 t, and we want to solve now for time because we're asked after how many hours. We're looking for the number of hours, we're looking for the time. All right, so again, the only tricky part about doing these problems, the first tricky part is being able to write that equation correctly, and then it's just reading the problem and interpreting the words and knowing which variable is which. That's half the battle, is being able to do that. The other half is now solving this equation, right? Because now we have an exponential equation that we have to solve for t. So if you haven't watched the videos that I did on exponential equations, you might want to check those out. First step to solving an exponential equation, get the base to the power by itself, right? The base to the power being this e to the 0.4t, which means dividing away the 500. Right? So if I divide both sides by 500, I'm going to end up with, I want to say 160. I'm going to pull out the calculator and double check that because I don't want to give everybody the wrong answers there. But 80,000 divided by 500, yes, it's 160. All right, good. All right, so 160 equals e to the 0.4t. So we isolate the exponential term, and then to cancel out the e, we use its inverse function, which is the natural log. All right, so I do the natural log on both sides of the equation. ln of 160, let me try that again. ln of 160 equals the natural log of e to the 0.4t. All right, I hope you can't really see that over there. Let me write this again. Put it down below. ln of 160 equals ln of e to the 0.4t. Right, so every time we're solving one of these equations that involves an e, which all of these ones that involve exponential growth and compound interest problems and radioactive decay, they all involve the e. So when we're solving these equations, we're always using that natural log, and you'll see it's a lot of the same mathematics each time. Right, so when I do the ln on both sides, the natural log actually cancels out the e on the right side, so I end up with now the natural log of 160 equals just 0.4t. Right? And then to solve for t, I divide both sides by 0.4. Right? So t is equal to the natural log of 160 divided by 0.4, which if you watch some of the other videos I did on solving exponential equations, that would give us the exact answer, ln of 160 divided by 0.4. But if I want to know how many hours it's going to take to get 80,000 bacteria, I'm not going to walk into the head biologist, my boss, and say, oh, boss, it's going to take ln of 160 divided by 0.4 hours until we have 80,000 bacteria, because who in the world knows how many hours that actually is? All right, so when we're solving word problems, we generally want to give our answers in a decimal form. Right? Approximate answers in decimal form are better than ln of 160 divided by 0.4 when we're trying to communicate our results to normal people who probably don't understand what that actually means. All right, so if I do ln of 160 divided by 0.4, I get 12.687, it looks like. All right, so let's call it 12.7 hours. All right, so after about 12.7 hours, our bacteria will grow to 80,000. Now remember, this is a model. It doesn't mean that after exactly this much time, we're going to have exactly this many bacteria. It's giving us an estimate of what's going on as time goes by, right? It's not like at this exact time, this is exactly how many we're gonna have. There are some fluctuations here and there on either side. All right, so that's how we solve when we have the number. We put that in here, the number of bacteria, and then we have to go through the steps of solving the exponential equation to solve for time. All right, I'm going to pause this one more time. The last part of this is to graph this function, which I'll just put the graph up here and then play the video again and talk about the graph for a few seconds. So the last part of this problem was to sketch the graph of the function n of t that we found back in part A. Now to sketch the graph, all I did was I took the basically 3 points that we knew. I knew that my initial value was 500. So when t equals 0, my point value was 500. So there's the point 0, 500. When t was equal to 10, I had 27,299, so I put that point up here. And when t was 12.7, I had 80,000, so that's that point up there. And then I connect those points to make that exponential graph. There's my graph of this exponential growth function of bacteria. All right, make sure you check out the other videos that I'm doing on the other applications of exponential functions.